Hello, my name is Kara, and I will be starting the group presentation for Newton's law of universal gravitation. So, to identify the topic and briefly introduce it, Newton's universal law of gravitation says that everything in the universe pulls on everything else, even if the objects are far apart. So the strength of this force, gravity, depends on how big the objects are and how far apart they are. So objects with more mass will pull more, and objects that are closer together will also pull more. So the law gives scientists a formula they can use to measure how strong gravity is between two objects. Newton's law of universal gravitation unifies celestial motion of planets and moons and terrestrial motion of falling objects under a single principle. So there's the story that Newton was inspired by the apple falling, and there's a picture depicting that. So relevant formulas and constants referenced. The formula for the law of universal gravitation is F equals g m1 m2 over r squared. So in this formula, F represents the magnitude of the gravitational force. G is a proportionality factor called the gravitational constant. M1 and M2 represent the masses of the first and second bodies respectively, and R represents the distance between the body's centers of mass. So the formula for G, the proportionality factor, is 6.674 times 10 to the negative 11th newtons times meters squared divided by kilograms squared. So the units on this are odd, but it's just so that you cancel out the units of the masses and the distance, and you just end up with newtons for the force. So gravitational acceleration near Earth's surface is given by G equals big G for the constant times mass of the Earth over r squared. So mass of the Earth is the mass of the Earth, and r is the distance from the Earth's center to wherever the object is that is accelerating towards the Earth. Using this formula leads to the commonly accepted value G, gravitational acceleration, is about 9.8 meters per second squared. And this image just shows how the distance and the masses of the objects relate to the force. Newton's law of universal gravitation is relevant to many different fields of science, but especially many fields within physics. It is a key part of physics because it explains how gravity works between objects, and it helps scientists understand forces that act both on Earth and in space. It's especially important in astronomy, where it helps explain why planets orbit the sun, why moons stay around planets, and how stars interact with each other. And ocean tides are caused by the moon's gravity acting on Earth, so that's also important. Newton's law is also used in engineering and space science to design satellites, spacecraft, and orbits, making modern space travel and GPS systems possible. So, gravity and the universal law of gravitation is important for a lot of different fields where you need to calculate gravitational force on objects, especially in outer space. And here's an image of the moon orbiting the Earth, and you can see it's causing these tides. So that is caused by gravity in a way that can be explained by Newton's law of universal gravitation. So relevant scientists thoroughly discussed. The main scientist who is relevant is Sir Isaac Newton, hence the name Newton's law of universal gravitation. But Galileo was also important. He was a predecessor to Newton, and he proposed that falling bodies and planetary motions share the same cause. So Isaac Newton built upon that and defined the gravitational pull. He actually defined it, and he used a mathematical equation to do that. And Newton believed in trying to express scientific truths mathematically. And to this end, he carefully studied the work of his predecessors, like Galileo, and he is known for his quote, "If I have seen further, it is by standing on the shoulders of giants." Newton's laws provided support for the belief that all of nature follows an underlying order.
Original experiment process described. Sir Isaac Newton was challenged by contemporary scientist Robert Hooke to prove his theories about orbits of the planet. Newton's original experiment process was largely theoretical, observational, not laboratory based like modern experiments. The process involved deriving equations that predicted motion outcomes, which were later confirmed by observation and calculation. Newton wrote his famous book Principia to prove these ideas. This work introduced a groundbreaking mathematical explanation of how the universe operates. Difficulties/complications explained. Planetary motions calculations required complex mathematics that were too difficult without modern computational tools. Gravity is extremely weak compared to other forces like electric forces, making it difficult to measure accurately. Newton lacked advanced instruments, so he could not directly measure gravitational attraction between small objects. In fact, the gravitational constant was not measured until Henry Cavendish experiment in 1798. Motion for experiment presented. The motion for studying Newton's law of universal gravity was to understand why objects fall toward Earth and why planets move the way they do in space. Scientists wanted to know if the same force that causes objects to fall also controls the motion of the moon and planets. Newton developed his law to explain this connection using mathematics and observation. His work helped show that gravity is a universal force acting between all objects with mass. Original benefits of discovery discussed. Newton's law gave an explanation for a celestial body motion. Previous models had limited accuracy and lacked understanding of mechanisms. Newton's universal theory of gravitation helped unify different observations of motion into one scientific explanation, such as falling objects on Earth and the motion of the moon and the planets in space. This showed the same force of gravity acts on all objects with mass. His work laid a much needed foundation for the continued development of physics and astronomy.
The modern experiment that scientists use, they test gravitational force by measuring mass and distance between objects, and they measure variables, apply the formula, and compare results. They use a couple of precise instruments to detect very small gravitational forces, which makes it more controlled and precise. And because this, the equipment they're using is very sensitive, the data is analyzed to confirm the inverse square relationship between force and distance. They repeat these experiments multiple times to reduce error. This helps confirm that the law works consistently. Difference in the modern approach to the law now, modern science still uses Newton's law, but it is now combined with more advanced theories like Einstein's theory of relativity for extreme conditions. Unlike early methods, modern approaches use highly sensitive instruments to measure very small gravitational forces. Data collection today is more precise and often supported by computer modeling and simulations. Experiments are repeated and analyzed statistically to reduce error and improve reliability. Modern studies often examine gravity on both very large scales like planets, galaxies, and very small scales. One big difference is the use of technology. Modern scientists use computers to simulate gravitational interactions. They also study extreme environments like near black holes. So Newton's law still works, but sometimes it needs to be combined with newer theories. And here I have an instrument, a modern instrument used for measuring the gravitational constant, which is housed in a vacuum system. And it measures the pull of 4 outer masses on 4 inner masses, as can be seen in the mock-up of the experimental setup. So a modern benefit of this law, we still use it today in space exploration. For example, it helps scientists calculate where satellites should go. Without it, GPS systems wouldn't work correctly. Engineers use it to calculate safe orbital paths for spacecraft and the satellites. It also helps us understand galaxies and large structures in space. It provides a foundation for more advanced physics theories used today, including astrophysics. So, Newton's law allows scientists to predict the motion of planets, moons, and the satellites. So the future expectations of research. Scientists continue to test Newton's law in more extreme environments, like gravity in extreme conditions such as deep space and near black holes. Future research focuses on connecting gravity with quantum physics to better explain very small scale interactions. More advanced technology allows for more precise satellite measurements and space-based experiments. Researchers use Newton's law as a foundation while exploring new theories and unanswered questions like dark matter and dark energy. The law is expected to remain important, but it's still relevant. It may be refined as new discoveries in physics emerge in the future. So that concludes the group presentation portion of my presentation. I hope you enjoyed.